Again, welcome to CS332 course. This is operating system course, which is given at Rutgers University, Newark. And this lecture will cover our course textbook, chapter 7, section 1 and 2, which is memory management requirements. So our main objective is to go through the memory management requirements. Example, what is relocation, protection, sharing, logical organization, and also physical organization. So first, we start with some three terminologies here. In memory management, we should know the term frame, also page and segment. In the section 7.4 of our course textbook, and also we're going to discuss the concept of paging and segmentation. So in terms of memory management, a frame means the face length block of a memory. So the face length block of a memory is called a frame. Page also is the face length block of data that resides in a secondary memory, such as the disk. So a page of data may temporarily be copied into the frame of the main memory. So again, the concept of a page, we are referring to the data that reside in a secondary memory. Now, the difference between main memory and secondary memory is that in the main memory, the data or the system is volatile. Volatile means when the computer goes off, again, we lost all the data. And normally CPU executes instructions from the main memory. So in order for an instruction to be executed or data to be used in execution, we must load the data. If we have it in our secondary memory, we must load it to main memory. So a secondary memory will be the permanent storage place, such as a floppy disk and Blu-ray and or the hard drive also. Now, segment means a variable length block of a data that reside also in the secondary memory. So a segment is the variable, not a fixed length. Variable length block means, again, the size may change, different size. The fixed length block of a data reside in the secondary memory is called a page. Then the variable length block of data that reside in the secondary memory is called a segment. So an entire segment may temporarily be copied into an available region of a main memory, which we call the segmentation. We will cover this topic in the future lectures. Or the segment may be divided into pages, which can be individually copied into the main memory. So again, here we say that in a uni-programming system, main memory is always divided into two parts. We have one part for the operating system, which is the kernel or the resident monitor. And also we have the other part for the program currently being executed. So again, in multi-programming system, the user part of memory must be further subdivided to accommodate the multiple processes. So when we have a unit programming system, again here, all the main memory will be divided only into two parts. But in multi-programming system, the user part of memory must be divided into subdivision to accommodate all the possible multiple processes. So if we have 5, 10 multiple processes, we should be able to again subdivide it. So the task of subdivision is carried out dynamically by the operating system. And also it's known as memory management. And that's the course and the lecture section that we are now. So an effective memory management is a vital in multi-programming system. A uni-programming system, and memory management is not much required because again, the main memory will be divided only into two parts. One part for the operating system, and the other part is for the program that is currently executed. But when we have a multi-system, where we can have more than one program executing at the same time. So we must make sure that, again, the main memory is subdivided among all the possible processes that's programmed in executions. So effective memory management is very important in multi-programming system. Now, if only a few processes are in the memory, then for much of the time, all of the process will be waiting for I/O, that's the input and output modules, and other process will be idle. So main memory needs to be allocated to ensure a reasonable supply of ready processing to consume available processing time. So again, while surveying the various mechanisms and also policies that are associated with main memory, it's very important to keep in mind that, again, the requirement that memory management is intended to satisfy. So this requirement is what is given to us, the relocation, protection, sharing, logical organization, and physical organization. This, again, is the main requirement for memory management. And as we said, again, a multi-programming system, memory management is very important, effective memory management. Because if we have 5 processes executing at the same time, they should be able to share the memory together, the main memory. So we start with the relocation. And here we say that as we know, in a multi-programming system, the variable memory is generally shared among a number of processes. So any number of processes that is using the CPU memory, as we all said when we are doing the CPU synchronize or process synchronization or CPU schedule, we know if you have a multi-programming system, or the process, if you have 2 or more processes executing at the same time, we should be able to, again, synchronize or a way to all the process to have access to the CPU. The same concept here also with the memory. We have a main memory. If we have 5, 10 process executing at the same time, we should be able to let them have access to the memory. So we share the memory among all the process. But typically, it also is very, or I would say it's not possible for the programmer to know in advance which other programs will be resident in the main memory at the time of execution of his or her program. It's very difficult to know in advance. So programmers typically do not know in advance which other programs will be resident in main memory at the time of execution of their program. So in addition, we would like to be able to swipe active processes in and out of main memory to maximize processes utilization by providing, again, a large pool of ready process to execute. Now, once a program is swiped out to this, it will be quite limiting to specify that when it is next swiped back in, it must be placed in the same memory region as before. Instead, we may need to, again, relocate the process to a different area of memory. So active process need to be able to be swiped in and out of memory in order to, again, maximize the processor utilization. And here we say specify that a process must be placed in the same memory region when it is swiped back in will be limiting. It's very difficult and limiting. So we may need to relocate the process to different area of memory. So that's the concept of, again, relocation. So instead of swiping in and out of a process, and now we are bringing the process back to the same location. It's possible, but the chance is very I would say it's very expensive computationally. So the best option and quicker is to relocate the process to different area of memory. So this example gives us the addressing requirement for a process. So we cannot know ahead of time when a program will be placed. And also we must allow for the possibility that the program may be moved about in the main memory due to swapping. So this first raised some technical concern related to, again, addressing. So that's, again, the diagram we have here, addressing. The diagram shows, again, a process image. We have the process control block, the program, data, and also the stack. And this is for simplicity. We should assume that the process image copies what? A contiguous region of main memory. Then clearly the operating system will need to know the location of process control information and also the execution stack, as well as the entry point to begin execution of the program for other process. So we have the process control information, the entry point to program, and the branch instructions, and also reference of data we are going to use. So with program, instructions, and data, we may do our execution. Then we have the top of the stack. Now, because the operating system is managing memory and is responsible for bringing this process into main memory, these addresses are easy to come by because, again, the processor must deal with memory references within the program. Branch instructions contain address to reference the instructions to the executed next. Also, data reference instruction contain the address of the byte or the word of data referenced. The process hardware and operating system software also must be able to translate the memory references found in the code of the program into actual physical memory address. And this will reflect the current location of the program in the main memory. So next we move to the concept of, again, protection. And each process also must be protected, again, against unwanted interferences by other processes. Relocation is very important because when, again, processes are swiping in and out, coming back in, getting the same memory space may be difficult or limiting. So that's the first requirement. We should be able to relocate the new memory space for the process. Protection also is very important. We always need to protect the process against any unwanted interferences by other processes, whether it's intentionally or accidentally. So programs in other process should not be able to reference memory locations in a process for reading or writing purposes without permission. So in one sense, satisfaction of the relocation requirement increases the difficulty of satisfying the protection requirement. The reason is because, again, the location of a program in the main memory is unpredictable. We cannot predict it. We can't know it in advance. So it is impossible to check absolute addresses at compile time to assure protection. And furthermore, again, most programming language allow the dynamic circulation of addresses at runtime. So memory references, again, generated by a process must be checked at runtime to ensure that they refer only to the memory space allocated to that process. Fortunately, again, we shall see that mechanism that support relocation also support the protection requirement. Normally, a user process cannot access any portion of the operating system, neither the program nor the data. And also, usually a program in one process cannot branch to an instruction in another process. And without a special arrangement, a program in one process cannot access the data area of another process. So these are all, again, the possible protections. We should also know that memory protection requirement must be satisfied by the processor, which is the hardware, rather than the operating system, which is the software. This is because the operating system cannot anticipate all of the memory references that a program will make. Even if such anticipation were possible, again, it will be prohibited, it will be a long, I would say, time-consuming. To be a time-consuming to screen each program in advance for possible memory reference violations. So next is sharing. Now we understand concept of relocation, protection, then sharing. So any protection mechanism also must have a flexibility to allow several processes to access the same portion of memory. That's the main memory. So for example, if a number of processes are executing the same program, it is advantageous to allow each process to access the same copy of the program, rather than have its own separate copy. So processes also are cooperating on some tasks may need to share access to the same data structure. So memory management system must therefore allow control access to shared areas of, again, memory, shared areas of memory. This mechanism also is used to support the relocation and also support the sharing capabilities. The next is the logical organization. So memory is organized as linear. Programs are written in modules. So almost main memory in a computer system is, again, organized as linear or one-dimensional address space, which normally consists of sequence of bytes or words. Now, secondary memory at its physical level is similarly organized. While this organization closely mirrors the actual machine hardware, it does not correspond to the way in which programs are typically constructed. So most, again, programs are organized into modules, some of which are, again, unmodifiable. It's only read-only and also execute-only. Now, if operating system and computer hardware can effectively deal with user programs and data in the form of modules of some sort, then the number of advantage can be realized. So here we can see the modules can be written and also compiled independently with all references from one module to another resolved by the system at runtime. Secondly, also with modest additional overhead, different degree of protection given to modules, that's read only, execute only, and also that can be given to different modules. And thirdly, also we say that it is possible to introduce mechanisms that by which modules can be shared among. So sharing on module level corresponds to users' way of viewing the problem. So the tool that most readily satisfy this requirement is segmentation, which is one of the memory management techniques explored in these lectures. So segmentation is the tool that most readily satisfy requirements. Then the next one will be the physical requirements. As we said again earlier, computer memory is organized into at least two levels, which is referred to as the main memory and secondary memory. So main memory provides the fast access at relatively high cost. In addition, also the main memory is volatile. That is, it does not provide permanent storage. But secondary memory is slower but cheaper than main memory and usually not volatile, which means secondary memory of large capacity can be provided for long-term storage of programs and data, while the smaller main memory holds programs and data currently in use. So again, the main memory available for program plus its data may be insufficient. If this case happens, then the programmer must engage in a practice known as overlaying. So again, that's the whole concept of a physical organization. So cannot leave the programmer with the responsibility to manage memory, and also memory available for program plus its data may be insufficient. Program does not know how much space will be available. And if it will be insufficient, overlaying allows various modules to be assigned the same region of memory, but it's time consuming to program. So in this case, a programmer must engage in a practice known as overlaying. So overlaying allows various modules to be assigned the same region of memory. So that will be the conclusion of these lectures. Again, these lectures will focus on main memory management requirements. As we mentioned again, we have 5 main requirements: relocation, protection, sharing, logical, and also physical organizations. So again, wish the class the best and thank you for your time.